Hello, welcome to the video of session 3 of module 2 filtering of long data sequences of the subject digital signal processing prescribed for 5th semester electronics and communication engineering students. Learning objectives of this session are we are going to learn filtering of long data sequences. And here we will be considering linear filtering concept. Then we will be getting the knowledge on block convolution. And at the end of this session, we will be learning how to do linear filtering operation using overlap add method. Let us begin our filtering of long data sequences. Let us consider a linear time invariant system with the system impulse response h of n. When we will going to say a linear time invariant system, or when we will be saying a system as linear time invariant, that system has to be linear as well as time invariant, right? So time invariant is nothing but irrespective of the time, whatever the input you are giving, the system is acting same in all instants of time. Obviously that will be time invariant. How we can say the system to be linear? If our system obeys superposition theorem, then we will be considering that particular system as linear time invariant system. Here our LTI system we are considering is basically acting as filter system. Basically here we are considering it as FIR system, as this particular system is not having any feedback in its structure. So our FIR filter is having its impulse response h of n, to which we are giving the long input data x of n. Suppose if we are giving the long input data which is x of n to this particular LTI system, output whatever we are getting here will be linearly convolved output of the sequences x of n and h of n. But in this particular case, the input whatever we are considering here is of larger length. So obviously using DFT method directly, it's difficult for us to find the linear filtered output. So because real-time signal monitoring applications, the signals, whatever the input signals we are considering is of larger samples, larger number of samples, and using linear filtering using DFT method, the signal must be of limited size because of the shortage of memory in our digital signal processor. So in real-time system what happens, the signal input has to be filtered out with impulse response to obtain signal output. It has to undergo a series of delays because of the data acquisition as well as data processing. So all say if we want to do that linear filtering operation using DFT, just by using FFT method of finding DFT, all the n samples has to be required simultaneously for our FFT system. But it is difficult. Complexity of n point FFT is n log n. So obviously the n is too large as for the long data sequences, then there is a delay or considerable delay in processing of these signals, which is a major hurdle for our real-time processing. So we need to think of an alternate way of filtering of longer data sequences. So the strategy whatever we will be considering in this particular case is we are considering that incoming signal which is of large in length, we will be considering that. Then we will be dividing that particular input into fixed number of or fixed size blocks before processing further. Okay. Next what we do is we will be computing linear filtering which is based on DFT of each block separately using FFT. Then Then what we do is, because of that computation of DFT based linear filtering of each block, we obtain output block or blocks of output. Then we will going to take, at the end we will be taking all the output blocks together such that we will be overlap the output value or the final output will be equivalent to the linear filtering of the incoming signal x of n directly. Main advantage of this particular method is samples of the output, which is y of n, which is equal to linear convolution of x of n with h of n, will be available real time block by block basis. So now the goal of this particular method is linear filtering or FIR filtering. Our system is nothing but FIR filter. The output of that particular FIR filter is linear filtered output y of n, which is the convolution result of x of n with h of n. So there are two approaches for the real-time linear filtering of long data inputs. So one method is overlap add method and another method is overlap save method. So in this particular video, we will be considering overlap add method. Before considering the overlap add method, we will be assuming certain things, pre-assumptions, that is the linear time invariant system, whatever we are considering, will be having its impulse response, FIR filters impulse response h of n is having m number of samples. So length of h of n is m. Then we will be assuming length of the block or the whatever the input signal we are dividing into block, that is having the length as L. Okay. Now let us considering filtering of long data sequences. So using as we considered, there are two methods. One is overlap save method and another is overlap add method. As we are doing both the methods, just by first we will be dividing the incoming samples into number of blocks, or we are segmenting it to number of blocks. Then we are convolving to obtain blocks of output, and at the end we will be fitting all the blocks of input such that we will be overlapping, and we may going to add, or we may going to keep as it is, or we may going to discard some values. So basically we are following block convolution operation here. So these two procedures are also called block convolution methods or operations, or they are also called segmentation method of linear filtering. Now, in this particular video or in this session, we will be learning overlap add method in detail. So, as we considered, our input to that LTI system is x of n, which is having length, which is having more number of samples. So, here LS number of samples our x of n is having. That is x of 0, x of 1, x of 2, x of 3 up to x of LS minus 1. And length of impulse response of that FIR filter is m they have given. So h of n is equal to h of 0, h of 1, h of 2, h of 3, h of 4 up to h of m minus 1. And see, as we considered, our x of n is long sequence. It is having more number of samples. So what we have to do? We have to divide x of n into blocks of data, that is xi of n. Each of the block is having L samples of this x of n plus m minus 1 number of zeros appended. Then whatever the blocks we are obtaining here, that has to be convolved with the given impulse response of the FIR filter to get the blocks of output yi of n. At the end, what we will going to do is, we will be combining all the output blocks. Here in this case, we will be employing overlap add method to obtain or to get the final output. So to understand this, let us consider an example where our x of n is having 18 number of samples, that is ls, value of ls is equal to 18. So our x of n is varying from x of 0, x of 1, x of 2 up to x of 18 minus 1, that is x of 17. Then the given h of n we will be considering as 4 samples in that h of n. So h of 0, h of 1, h of 2 and h of 3. What we have to do now? We have to make length of the input blocks. Whatever the input we are dividing into number of blocks, that block should be consisting of n number of samples. So we are assuming our blocks to be of length 7 here. Then if we, as we are assuming it as 7 and the length of the given impulse response is 4, value of L, that is number of values L to be n minus m plus 1. So n is 7 minus 4 is 3 plus 1 again is 4. So we have to divide x of n into number of blocks such that each block is having 7 samples in it. So first what we have to take? So first block we have to consider first L samples of x of n. Then m minus 1 zeros has to be appended at the end in all the blocks. Okay. So first x of 0, x of 1, x of 2 and x of 3, that is 4 samples. First 4 samples of the x of n. Then m minus 1 number of zeros. So 4 minus 1, that is 3 zeros here. See, in blue color I have highlighted these 3 zeros. Blue zeros are appended zeros for the first block. Similarly, second block will be consisting of the remaining samples, remaining L samples, that is 4 samples, x of 4, x of 5, x of 6 and x of 7. This has to be appended with number of zeros such that the length of this particular block will be 7. So again 3 zeros we are appending here. Similarly, next block x of 3 is having x of 8, x of 9, x of 10 and x of 11, the 4 samples from the incoming long data sequence, and these 3 zeros are m minus 1 zeros appended. So similarly x4 of n is the remaining values of this remaining 4 values are next 4 values we can say x of 12, x of 13, x of 14 and x of 15, and this has to be appended with 3 zeros, that is m minus 1 zeros, such that x4 of n is also of length 7. Last, it is our x of n is having up to 70, because totally there are 18 samples. So remaining samples from this are 16 and 70. So only 2. But we have to have a length of that particular block is 7. So to make the length of this last sample or last block, we have to append 5 zeros. See, the zeros which is in blue color are all these zeros, blue zeros are appended zeros to these blocks of data to make the length is equal to 7. So this is the first method to be followed for dividing the long data sequence x of n into number of blocks. What's the next step? We have to make the length of the given impulse response, which is to be equal to length of blocks. So what's the length of impulse response? It is m. But we have to make length of h of n, which is also equal to n, such that this n samples blocks has to be directly convolved with the n samples of h of n to obtain our yi of n. So as h of n is having the samples h of 0, h of 1, h of 2 and h of 3, we have to make length of this to be 7. So remaining how many numbers? 4 minus 1, 3 zeros to be appended to make the length of our h of n, which is equal to 7. So what's the next step? Now we have divided into number of blocks. Then we made the length of h of n to be equal to length of block. Next we have to convolve, as number of samples in each block is 7 and we made the length of our h of n also equal to 7. Now we need to take 7-point circular convolution of each block of input with our impulse response. Okay. And here y1 of n, we obtain y1 of n by 7-point circular convolution of x1 of n and h of n. Observe here, we have some of the samples in green color, some of the samples in saffron color, some of the samples are in blue color and some are in cyan color. Okay, so let us check why we have these many colored samples. I just tell, observe here, y1 of n is equal to x1 of n, which is 7 points circularly convolving with h of n to obtain y1 of 0, y1 of 1, y1 of 2, y1 of 4, y1 of 3, 4, 5 and 6. So there are 7 samples. Similarly, y2 of n is equal to 7-point circular convolution of x2 of n with h of n to obtain y2 of 0, y2 of 1, y2 of 3, y2 of 4, y2 of 5 and y2 of 6. Similarly, y3 of n can be obtained by 7-point circular convolution of x3 of n and h of n. So we obtain y3 of 0, y3 of 1, y3 of 2, y3 of 4, y3 of 5 and y3 of 6. Similarly, y4 of n can be obtained by x4 of n circularly convolved with h of n to obtain y4 of 0, y4 of 1, y4 of 2, y4 of 3, y4 of 4, y4 of 5, y4 of 6. Okay. And last block of output is y5 of n obtained because of 7-point circular convolution of x5 of n with impulse response h of n. So here our output block is having the samples y5 of 0, y5 of 1, y5 of 2, y5 of 3, y5 of 4, y5 of 5 and y5 of 6. And observe in this things to be considered. We have to concentrate here. We are not just doing overlapping and we are keeping some values, or we are not doing just overlapping and discarding some values. Instead, we are keeping some values as it is and we are doing some adding operation or adding some samples. Okay, carefully observe, because this is the overlap add method of doing linear filtering operation. These 4 values or 4 samples which I have highlighted in green color, we are keeping as it is. You can observe here, final output is y1 of 0, y1 of 1, y1 of 2 and y1 of 3. We are not doing any manipulations here. We are not doing any mathematical operation. Simply we are keeping these samples as it is. But observe, what we are doing is, we are considering this m minus 1, that is m value here it is 4. So 4 minus 1 is 3. 3 samples are getting added with first 3 samples of the next block. That means last m minus samples of first block is getting added with first m minus 1 samples of the next block. So this sample, saffron colored sample is getting added with saffron colored value of the next block. Blue color sample is getting added with blue color value of next block. Cyan colored sample is getting added with the next cyan color of the next block. See, these are added. See, y1 of 4 plus y2 of 0. You can observe here. And y1 of 5 plus y2 of 1. y1 of 6 plus y2 of 2. This one. Next, we are keeping this as it is. So it is in green color, y2 of 3. Next, we are adding y2 of 4 with y3 of 0, y2 of 5 with y3 of 1, y2 of 6 with y3 of 2. Okay. Next, y3 of 3 we are keeping as it is. Next, y3 of 4 is adding with y4 of 0. y3 of 5 is adding with y4 of 1. y4 of 2 is adding with y3 of 6. We are keeping y4 of 3 as it is. Then y4 of 4 is added with y5 of 0. y4 of 5 is added with y5 of 1. and y4 of 6 is added with y5 of 2, and these values we are keeping as it is again. It means y3 of y5 of 3, y5 of 4, y5 of 5, and y5 of 6. This is for general, or this is a general example we have taken. So now for better understandability, let us take some illustrative examples with the sample numerical samples. So before that, so how we are doing here in this overlap method is incoming signals we will be considering. So first L values of well samples of x of n we are taking. To that we are appending m minus 1 zeros to make length of this block as capital N is equal to L plus m minus 1. Similarly, second block we will be starting with the L after L plus 1 value, whatever we will be putting, that L values number we can take, we will going to take. Then to that particular samples we will be appending m minus 1 zeros such that this block, the second block, is also having the length n, capital N, which is equal to L plus m minus 1 samples. Similarly, the x3, it is also having L samples from x of n and m minus 1 appended zeros. Okay. Now, after segmenting or after dividing into number of blocks, we will be circularly convolving these blocks with h of n, that is impulse response, to obtain block of output these values. y1 of n is having L plus m minus 1 samples. Similarly, y2 of n is having L plus m minus 1. And similarly, y3 of n is also having L plus m minus 1. But because of these appended zeros at each incoming sample or input blocks, if we add these two, what we will be doing is we are keeping this n sample as it is, to which last m minus 1 sample of previous sample is overlapped with first m minus 1 sample of output block of second output block. Okay. Similarly, second blocks m minus 1, last m minus 1 samples will be overlapped with first m minus 1 samples of the third block. So what we do is overlap, and then we will be adding these m minus 1 samples here and here. Okay. This is the strategy we will going to follow in this overlap add method. Now let us take an illustrative example. Here the problem statement says, consider a FIR filter with impulse response h of n is equal to 3, 2, 1 and 1. If the input sequence x of n is equal to 1, 2, 3, 3, 2, 1, minus 1, minus 2, minus 3, 5, 6, minus 1, 2, 0, 2, 1. Find output using overlap add method. Assume length of block is equal to 7. So what we have to do? We have to find the output, that is linear filtered output of the given incoming sample, which is having more number of samples, longer data. So we have to make use of the block convolution method, that is overlap add method, for finding the linear filtered output or overall output. Sorry. So what they have given is they have assumed us to assume the length of block to be 7. So given there it is a value of n is equal to 7. What they have given x of n, which is 1, 2, 3, 3, 2, 1, minus 1, minus 2, minus 3, 5, 6, minus 1, 2, 0, 2 and 1. So totally there are 16 samples in this particular incoming sample. So value of LS is 16. And they have given the impulse response of this particular FIR filter, which is h of n, that is 3, 2, 1 and 1. So length of this h of n is 4. So n value they have given us to assume as 7 and value of m as 4. So 7, if we substitute a value of n as 7, what we will going to get obtain as L, n minus m plus 1. So 7 minus 4, 3 plus 1 is 4 again. Now we have to divide the input samples into number of blocks. So what we will be doing is, we are dividing each block such that each block is having n number of samples, where first L samples are the samples from the incoming or input signal x of n, and m minus 1 appended zeros. Okay, we can observe here value of L here it is 4. So 4 samples of x of n, which is appended with m minus 1. So value of m is 4. 4 minus 1, that is 3 zeros. These 3 zeros are appended zeros, such that the length is having 7. Value of capital N is 7. Similarly, x2 of n is having next 4 samples of x2 x of n, 2, 1, minus 1 and 2. And these 3 zeros are appended zeros to make length of x2 of n as 7. Next, x3 of en block, third block of input, this is generated block, is having next 4 samples, that is minus 3, 5, 6 and minus 1. This is appended with m minus 1 zeros, that is 3 zeros, to make length of x3 of n is again 7. Similarly, last block of input, that is x4 of n, which is having next 4 samples of x of n, that is last 4 samples we can say in fact, 2, 0, 2, 1, which is appended with 3 zeros, such that total length of this particular block is also 7. So, next step is, we have to make length of the impulse response of the given FIR filter to be equal to n, which is equal to L plus m minus 1. They have given the samples, number of samples in the h of n is 3, 2, 1, 1, that is 4. We need to make the length of that h of n as 7. So, we need to append 3 zeros. Okay, we need to append 3 zeros to this given h of n, such that our h of n should be having, totally there are 7 samples in it. So what is the next step? Next, we have to find the circular convolution of blocks of input with the impulse response of the given FIR filter. So, first output block will be obtained by 7-point circular convolution of the first input block and the impulse response. So, we obtain the output block samples as 3, 8, 14, 18, 11, 6 and 3. And we obtain second block of output by 7-point circular convolution of x2 of n with impulse response h of n. The output block y2 of n is having the samples 6, 7, 1, minus 5, 4, minus 4, minus 3 and minus 2. Next, our y3 of n can be obtained by convolving 7-point circular convolution of x3 of n with h of n. We obtain the values minus 9, 9, 25, 11, 9, 5 and minus 1. Similarly, fourth output block will be consisting of the 7-point circularly convolved thing of x4 of n with h of n. So, our y4 of n is having the samples 6, 4, 8, 9, 4, 3 and 1. So, these are the blocks of output obtained by 7-point circular convolution of blocks of inputs or input blocks with impulse response of the FIR filter. So what now exactly we are doing is, we are keeping these blocks of data. See, observe 7 values here. First block of data. This is second block of data, third block of output, fourth block of output. So we are keeping like this. See how we are keeping is last m-1 sample to be get coincide with first m-1 samples of the second block of output, and last m-1 sample of second output block should be coincide with first m-1 sample of the third block. Similarly, last m-1 sample of third block is coinciding with the first m-1 sample of the fourth block of output. See, we have written like that. Then what we need to do is the overlapped values or overlapped samples has to be added. The samples which are not coincided can be kept as it is. You can observe here in the blocks or in the samples of blocks of output or output blocks, the samples which are represented, highlighted in green color, we will be keeping as it is. Cyan color values are getting added with the next cyan color. Saffron colored samples are adding with next sample saffron color. Similarly, red colored samples are adding with the next red color sample. See, first green color, see 3, 8, 14, 18 as it is we are keeping. L minus 1 samples. M minus 1 samples. Last M minus 1 samples are 11, 6, 3. First M minus 1 sample of second block is 6, 7, 1. These are coinciding and we are adding this. So 11 and 6 is 17. 6 and 7 is 13. 3 and 1 is 4. Minus 5 is not coinciding with anything. So we are keeping as it is. Minus 4, minus 9. So it is minus 13. Minus 3 plus 9, it is plus 6. Minus 2 plus 25 is plus 23. Sorry. 11 is not coinciding with anything. So we are keeping 11 as it is. 9 with 6. So it is 15. 5 plus 4, it is 9. Minus 1 plus 8 is 7. But again observe in the last block of output, 9, 4, 3 and 1 are kept as it is. So total output of our FIR filter, otherwise the complete linearly filtered output of the given FIR filter is nothing but y of n, which is equal to 3, 8, 14, 18, 17, 13, 4, minus 5, minus 13, 6, 23, 11, 15, 9, 7, 9, 4, 3 and 1. Similarly, let us consider another example for better understandability. So this makes us be clear in this overlap and add concept. Okay. So the problem statement what they have given is, consider if FIR filter with impulse response h of n is equal to 1, 1, 1. If the input sequence x of n is equal to 3, minus 1, 0, minus 3, 5, 6, minus 1, 2, 0, 2 and 1. Find output using overlap add method. Assume length of block is equal to 5. So let us solve this. So let us find the linear filtering. Here they have given us to assume length of block as 5. So value of n to be assumed as 5. And given value of x of n is 3, minus 1, 0, minus 3, 5, 6, minus 1, 2, 0, 2 and 1. So there are 10 number of samples. So length of the given input is ls, which is 10. Similarly, the given h of n is 1, 1, 1. So there are 3 samples. So value of m is 3. And assumption, it is value of n is equal to 5. Sorry, they have given length of block as 6. So we have to consider value of n as 6. And from this we can see m value of m is 3. So L value of L can be obtained by N. N is 6 minus 3 is 3 plus 1 is 4. Yeah. So now we have to divide the incoming sample or input sample x of n into number of blocks such that each value is each block is having n number of samples. N value we are assuming it as 6. So sorry. L value is 7. L value of L we found it as 4. So first 4 samples is appended with L minus 1 number of zeros, that is 2 zeros, such that length of block is 6. So x1 of n is 3 minus 1 0 1 0 and 0. X2 of n, the second block of input, which we obtained by first considering L number of samples appended with m minus 1 number of zeros. So 3 2 0 1 with 0 and 0 appended. Next the remaining values, that is 2 and 1. So to make the length of x3 of n to be 6, we have to append 4 zeros at the end of this particular block. So this is how we are dividing our long input sequence x of n into 3 blocks of input data, that is x1 of n, x2 of n and x3 of n. Next, what is the thing? We have to make length of the impulse response, which is to be equal to length of input block or segmented block length. So now h of n, what they have given is 1 1 1. So that is 3. But we have to make length of that h of n to be 6. We have to append remaining zeros. So it is 3 zeros we need to append to obtain h of n is equal to 1 1 1 0 0 and 0. So next we have to convolve circularly this block of inputs with impulse response to obtain blocks of output. Okay, that is yi of n. So y1 of n can be obtained by 6-point circular convolution of x1 of n with h of n. We will go. How we have to do this is we have to generate x1 of n, that is square matrix, and we have to multiply directly that square matrix with the column matrix h of n. We obtain this, that is samples of the first output block. So y1 of n is having 3 2 2 0 1 and 1. Similarly, second block of data can be obtained by 6-point circular convolution of x2 of n with h of n. So x2 of n will be considering, or we are generating the square matrix, and that will be directly multiplied with the column matrix h of n. We obtain the samples 3 5 5 3 1 and 1 of our second block of output. And similarly, last block, that is y3 of n, last output block y3 of n can be obtained by 6-point circular convolution of the third block of input with the system impulse response h of n. So square matrix x3 of n will be multiplied with the column matrix h of n to obtain the samples 2 3 3 1 0 and 0. And here also you can see the colors of these samples. So samples which are in green color we are keeping as it is, and others colors or corresponding colors are adding here. So before that, what we will be doing is we are keeping one below the other such that last m minus 1 sample of previous block is merged with first m minus 1 sample of next block of output. See, first y1 of n we are keeping as it is 3 2 2 0 1 and 1. So m value here it is 2. Sorry, L minus L value is 2. Sorry, 3. So L minus 1 is 2. 2 samples are merged with the first 2 samples of the next block. Either you have the 3 and 5. So we are keeping 3, 5, 5, 3, 1 and 1. Similarly, last L minus 1 samples are coinciding with first 2 samples of the next or the final block. So 2, 3, 3, 1, 0 and 0. Now we are overlapping these. Then as these are not overlapping with any of the value, we are keeping as it is. And the samples which are overlapping each other are getting added here. So 3, 2, 2, 0. Okay. 1 and 3 is equal to 4. 1 plus 5 is equal to 6. 5 and 3 are not overlapping with any values. So we are keeping as it is. 1 plus 2 is equal to 3. 1 plus 3 is equal to 4. 3, 1, 0, 0, we are keeping as it is. Okay. So the final output or the linear filtering of the given FIR filter is Y of n is equal to 3, 2, 2, 0, 4, 6, 5, 3, 3, 4, 3 and 1. Here we are not considering these zeros. As they are zeros, they are generated because of the zeros whatever we appended in the incoming samples or input blocks. So we can neglect these values. So this is the output of the given FIR filter. So in this session, the learning outcome, whatever the knowledge we got from this are, so we first considered filtering of long data sequences, that is for real-time signal processing. Okay, as they are longer than data length, we are considering this. So LTI system output, which is linear filtering. Next, we considered block convolution, how we are doing here, how we are convolving here, just by considering the incoming samples into number of blocks of inputs and convolving with impulse response to obtain blocks of output, then overlapping and all those things. Okay, so and we concentrated more on the overlap add method here, and we considered some numerical examples or illustrative example for better understandability. I hope you understand the concepts whatever we discussed here. So far, to check how we understood the concept, let us have some of the multiple choice question here. Try to answer here. So overlap add method is one of the options: block convolution method, segmentation convolution method, or both of the above, none of the above. What's the answer? So how we will be doing? We are segmenting the longer data input into blocks of data, right? So our overlap add method is also known as block convolution method, or it can be known as segmentation convolution method also. So obviously the answer is both of the above. So answer is option C, both of the above. So next question. Overlap add method is also known as overlap discard method. Options, let us check. Is it true or false? We are not discarding anything here. Instead, what we are doing is we are merging, overlapping, and we are adding. Right? So the answer is false. Option B is the answer. So overlap add method is not a overlap discard method. Let's go to the next question. Overlap add method is real-time linear filtering approach. Is it true or false? Yes. Why we consider this session? As for the real-time signal processing application, the output of the LTI system is obviously linear filtering. It is difficult or it is a hurdle to use FFT techniques for finding this linear filtered output. Instead, what we are going to do here is we are making use of segmentation method or block convolution method for finding that linear filtering approach or linear filtering for the real time. Right? So our overlap add method, obviously a real time linear filtering approach. This is the answer. So it is true. Option answer is It is option A. Last question of this session. In overlap add, which of the following is incorrect? Let us check the options. Option A, overlapped values has to be added. Next option, it will include adding a number of values in the output. It can be computed using linear convolution. Overlap add and overlap save are almost similar. What is the answer? Yes. So, in overlap add, which of the following is incorrect? First option is overlapped values has to be added. Second option, it will include adding a number of values in the output. Can be computed using linear convolution. All of the above. Obviously, as we saw from the discussion in the session video, the values, overlapped values are adding here. Also, it includes the adding of number of values in the output section. That's also correct. And it can be computed using linear convolution. Correct. So, we are computing using linear convolution by circular convolution method. So, all answers are correct. So, the answer is the option D, which is all the above. Hope you enjoy or you gain the knowledge from this video session. For more details, you can refer to the book written by Prokis and Monolokis, a book called Digital Signal Processing Principles, Algorithms and Applications. And the book written by Lee Tan and Jean Jiang, Digital Signal Processing Fundamentals and Applications. And the books written by Mr. Uday Kumar is the name Digital Signal Processing. Thank you.